These notes are posted on Canvas, but I want to walk through them with you so you understand more a little bit about what you're looking at. So first off, the focus of today is the photoelectric effect. And the photoelectric effect, you should have already watched the pre-flight on it, so you should be familiar with it. And to sum it up, what it demonstrated is that the energy of light is contained in the frequency of the light wave as opposed to the amplitude. That's completely opposite of how mechanical waves work. The consequence of that means that when light interacts with physical matter, it does so like a particle. So there's some key things we need to talk about today. Sorry, you got the bell from school as I'm recording this here. From your equation sheet, I clipped off the section on electromagnetic waves. You should be familiar with V equals lambda F. We've substituted the letter V with the letter C for the speed of light, which is 3 times 10 to the 8th meters per second. You should be familiar with the period of a wave equals 1 over the frequency. Now the new things, E equals HF and K max equals HF minus phi, which is the work function. So I want to point out HF appears in both of these equations. They mean the same thing. They're the energy of a photon. A photon is a particle of light. That energy is dependent upon H, called Planck's constant, which there are two numbers, I'll just discuss why in a moment, times the frequency of the light. Now, we're going to end up with 2 units of energy, E equals HF, joules, which you're familiar with, and electron volts, which you're not. E capital V, shown here, that stands for electron volts. We'll talk about what electron volts mean in a future class, but for now, it's a unit of energy. 1 electron volt equals 1.6 times 10 to the negative 19th joules. All right, so E equals HF. Anytime you're running this equation, what you're doing is you're solving for the energy of light. Let's say you're given the wavelength lambda. The first step would be to run the speed equation, V equals lambda F, where you would use 3 times 10 to the 8th for the speed, and then whatever they gave you for the wavelength to solve for the frequency. Then you can take that frequency and run E equals HF. H, known as Planck's constant, there's 2 values because you have 2 units of energy, joules and electron volts. So 6.63 E negative 34 joule seconds or 4.14 E negative 15 electron volt seconds. Both of them work for H. How do you know which one to use? Depends on what they want as their unit of energy, which we'll see in a little bit. F is the frequency measured in hertz. Now, let's talk about the second equation. K max equals HF minus work function. Effectively, what's happening is you have a piece of metal, and that's where the work function comes in. The work function describes how much energy is required to eject an electron. So we'll put our happy little electron right here. Put the negative sign on it to indicate that it's an electron. Incoming light wave hits this electron. That is your E equals HF. The HF in the function, the incoming energy. If HF is bigger than the work function, the result is the electron, boom, gets ejected. The electron is ejected. And that means it's moving, which means it has a velocity or kinetic energy. That's where K max comes in. The kinetic energy of that electron, of that ejected electron. That should say ejected electron. In joules or electron volts. Okay, so let's go through some examples. Number 1 on your WebAssign is just going to be about solving for the energy of the photon. There's going to be quite a bit of conversions on this. You're going to see kilohertz, megahertz, nanometers, So have the equation sheet ready when you do the homework. You see here in example 1, it's asking us what is the energy of the photon in joules and in electron volts. First thing, I have to convert the 1280 kilohertz into hertz. To do so, I multiply by 10 to the third. I get 1.28 hertz, or 1,280,000 hertz. To do it in joules, I will use the H value of 6.63 E negative 34, as shown here, multiplied by the frequency, and I get the energy in joules. For electron volts, same equation. The difference is I'm using the 4.14 E negative 15. The alternative is just to directly convert from joules to electron volts. 1 electron volt, shown here, is 1.6 times 10 to the negative 19th joules. That again is found on your equation sheet. Converting from joules to electron volts, I still get 5.30 E negative 19 joules. Question 4, I'm not going to solve for you, but I am going to show you the process. So question 4 from the Web of Science says the longest wavelength. I want to point out longest wavelength is the same thing as saying the smallest frequency or lowest energy. The longest wavelength or lowest energy for zirconium in order to eject an electron is 4.05, means that you have to have at least 4.05 electron volts of energy to eject an electron. Binding energy, that means the work function. So the question is asking, well, what's the wavelength for that particular electromagnetic radiation? So I need 4.05 electron volts. So E equals HF. I'll find the frequency. But then I have to find the wavelength. So what I'm going to do is use the speed of light, c, equals lambda f, solve for the wavelength. The final step, if you'll see here on WebAssign, it wants the answer in nanometers. So I'll convert my wavelength from meters to nanometers by dividing it by 10 to the negative 9th. The last question is this in the visible range? The visible range of light, meaning can you see it with your eyeballs? Roy G. Biv, that's your colors. Red, 700 nanometers, violet, 400 nanometers. As I go from 700 to 400, the wavelength gets smaller, which means since wavelength and frequency are inversely related, the frequency gets larger. And since the energy depends directly on the frequency, if the frequency gets larger, then the energy also gets larger. Moral of the story, what you're going to do when you find that wavelength is see, is it between 400 and 700 nanometers? If so, check yes. If not, check no. Question 5, similar idea, binding energy of mercury. So that's looking for work function. Longest wavelength, that's the lowest energy. This time, you're given the wavelength and you're asked to find the energy. So you're actually going backwards on what you did in question 4. 277 nanometers, convert it to meters, find the frequency using the speed equation, find the energy using E equals HF. You're literally going backwards from what you did in question 4. Question 6, our last unique one. You have ultraviolet radiation given wavelength, landing on uranium, ejecting electrons. So if these are ejected electrons, that means it's K max. That's a kinetic energy. The electrons are moving. Moving means they have velocity. Velocity means they have kinetic energy. That's the kinetic energy of the electrons. What is the binding energy of the metal? That's the work function. That's what we're trying to solve. So I'm going to go ahead and take the wavelength and find the frequency. C equals lambda f. Number, nanometers, so I need to do the times 10 to the negative 9th. I get the frequency of light. Once I have the frequency, I need to know the energy. Why am I using 4.14 E negative 15 instead of 6.63 E negative 34? Because it wants the answer in electron volts. So I find out that my ultraviolet radiation, UV radiation, is 3.83 electron volts. The kinetic energy of the ejected electron is 0.197 electron volts. I supplied 3.83 from my light, solve for the work function. I find the work function was 3.633 electron volts. What that means is every single particle of light that is greater than 3.633 electron volts will strike the metal and eject an electron. If the incoming light has less energy than 3.633, that means the light wave would fail to eject the electron, and the light wave would simply either bounce off or pass through the metal. The electron does not absorb the energy and then wait for another particle of light to strike it. It does not work that way. The electron can only absorb energy from one photon at a time. So you cannot say, I'll have two smaller photons, have it hit the same electron and eject it. It does not work that way. That's a wrap.